Indeed, I'm going to talk about imitation learning and reinforcement learning. I just want to give you kind of an overview on the field, so it's educational, and how we can combine them to actually solve some previously intractable tasks. So indeed, as you said, I'm a senior scientist at Philips Research. I'm also at TUE. I have kind of a diverse background. I work on 3D scanning technology, biomedical data analysis, and so on. And at Philips, I'm working on AI applied to MR. So indeed, I presented last year. You can find here the PyData talk. And if you're interested, come talk to us. So it's pretty cool stuff we are doing there. At TUE, I'm focusing more on efficient and explainable AI. So here's something that I did at Google on how to understand what's going on inside a deep neural network, and I will also get back to that later. I also have others, so please feel free to reach out later. But now, something completely different. So I'm going to talk about imitation learning, reinforcement learning, and then I will use the bot ball competition to kind of explain them how you can combine them, and specifically with the bot that I developed, which is called MimicBot. And I promise you, I don't have equations on the slides. So it's a good sign. So what is imitation learning? What is reinforcement learning? So I really like this picture. It's from a recent paper. Let's assume you have an environment. It can be a video game, a simulation of a machine, like a Philips scanner, SML machine, or actually a user working on a web page. You have this environment. Now you want to have an agent to be able to operate in this environment and take actions and modify the environment. So how do we train these actions? So we can take the imitation learning route, and we have an expert, like a human, also interacting with the environment. And the human receives some observations, so look at the environment, and take some actions. Now, what we can do, we can have a model in between that is just perceiving the same as the human is doing and taking the same actions. So in a way, it's like a classification task where you want to learn, just try to predict the actions that the human is doing. Okay, so that's kind of one approach. The other one is what you do with reinforcement learning. You still have your observations, we call them state, and we need to take some actions as well to interact with the environment. But now we don't have an expert that is telling us how to actually do these actions, right? So at the beginning, the agent usually takes just random actions. So it can just do something and probably will fail because there is no notion of the task that it has to perform. Think about driving a car or playing a video game. So the difference here is that the environment gives a reward signal, which can be how far you are from your end goal during driving a car, right? So, or how close you are to the middle of the road, or your score in a video game. And this reward is then used to train your agent. So if you get high reward, you are basically trying to give incentives to the agent to continue doing this good action given the current state. And this is rather complicated stuff, but now in a few recent years, improved a lot as a methodology. I'll get back to that later. So this is kind of the setting. And let's get started with imitation learning. You have a lot of different applications, so different implementations. I will just talk about one, which is behavioral cloning, which is extremely simple. Is basically the most simple approach that you can have. And if you have an environment, you can code it like in just a few hours, right? So it's super simple. What you just do, you just take the observations that the user, the expert is having, and you just take the action that the expert is doing on the environment, and you just treat it as a classification problem. Again, so you just collect them, and you just train if you have your classifier that can be implemented in with the traditional methods or deep learning. It's rather straightforward approach that you can take. And actually, this is a rather old methodology. Actually, the first paper on this is from 1995, presented at NeurIPS. And actually, funny thing, it was already a neural network-based approach. And here, basically, they had, it was based on self-driving cars, one of the first approaches there. So you had a human driving, a camera on the car. The camera was then a very small video, 30 by 32, which then was used to put into a neural network, and the network had to predict the action that the user was taking, how much he was steering the wheel. Okay, so that's very simple approach, but also doesn't work all the time. And here's the explanation. Yeah, so you may have that your agent is not really seeing all possibilities that you have in the real world. So this is a funny GIF that I found very closely matching what I wanted to say. So let's say that you have your car, your driving car in your environment, and you ask the expert to drive it around. So what they usually do, they do something reasonable, right? So they just stay in the middle of the road, and they maybe just go a bit outside. But let's say now you have your agent that you're just trying on this distribution of trajectories that you have. And at some point, for some reason, it's not perfect, it's just drifting a bit. So as you can see there, the red line. As soon as it drifts a bit, yeah, it has no data because the expert never tried to go so far out of the road, right? And then you basically have a catastrophic failure because the agent never saw an example like that. So that's the main issue with behavioral cloning. In the overall imitation learning, there are other approaches that try to address this, but they tend to go in the direction of reinforcement learning. Okay, so I found this tutorial at ICML 2018 very insightful. So if you want to dive a bit deeper, I recommend to have a look. The videos are on YouTube, and also the slides are online. So if you want to dive a bit more in the topic, yeah, you can go there. Okay, so that's about imitation learning. Let's have a look now at reinforcement learning. Reinforcement learning became rather famous recently because of several things that happened. It's basically the engine behind AlphaGo, the algorithm from DeepMind, which is like the AI research lab from Google, that won against Lee Sedol in Go. And Go is this board game that was previously thought intractable because it's a very large board game compared to chess, where you have way more actions that you can take. And yeah, so that's basically, well, AlphaGo was the first one, and then we had AlphaZero, which is, again, an extension of AlphaGo that can be deployed, and it's actually relying more heavily on reinforcement learning than AlphaGo. And what I wanted to show there is that this AlphaZero is just one single algorithm. It's like a blueprint for an algorithm that can act in an environment. The environment here is the board game. It can be chess, it can be shogi, can be Go, right? So the environment is the board game. You can think about a position, like a move, an action that you can take in this environment. And the same algorithm can be then trained to actually act on these different environments. And here you can see, okay, the green bars are basically telling you that AlphaZero can actually beat the best stockfishes, like a chess engine, but also in other board games like shogi and Go. And it's the, let's say, the state of the art. All right, so, but you can go beyond that. We're just looking at the board games. You can also have it in the real world. You can do an interplay with, for example, with robotics. And this is a work from OpenAI, where they actually took this manipulator that was not really, in a way, funny thing, it was not very successful, this manipulator. It's a commercial product that was not selling because it was too difficult to control. And that's actually, they showed that you can actually control it now with a reinforcement learning approach if you simulate. So you simulate your manipulator in a virtual environment. You do the task, in this case was rotating the cube and showing different letters, and also doing, for example, pivoting, like rotating the cube, sliding in the end, or just using the finger to rotate it in this direction. So yeah, you can go here. There are a lot of cool videos. And it was a nice approach because it showed that you can do the simulation in a virtual environment and then go to the real world, do some adaptation, and still have some good performance. And the reason why I want to show this is actually that why go in the virtual environment in the first place, right? Why don't we do just reinforcement learning with the real object? And the reason for that is that one key drawbacks of reinforcement learning is that it's very sample inefficient. It means that in order to understand what to do, you need to do a lot of trial and errors. So you just do some action, you fail, and the reward is negative, so you stop doing that action. You get a new one that is good, and then you get a positive feedback. But then again, you reach a new point where you don't know what to do, you fail, negative reward, and you continue like that. And it's a very lengthy process. So, and indeed, so we try to go more and more on simulations, and so that we are more efficient. If you want to dive a bit deeper, I recommend this book. It's Reinforcement Learning in Introduction by Sutton and Bartle. It's a very good one. And it's also it's really looking at the whole field from the very early. If you know about dynamic programming, you can actually see it as a case of reinforcement learning, or use it for solving a reinforcement learning problem. You can have these Monte Carlo methods that are heavily based on randomness. And nowadays, the most used one is called temporal difference learning, for which deep reinforcement learning is part of. And I'll go a bit deeper on deep reinforcement learning. But again, so this is the book. And the cool thing about the field is that nowadays, all the fancy algorithms are implemented in using Python. And we have very good baselines. So this stable baseline repo, it's fantastic. Basically, all the state-of-the-art reinforcement learning agents are there. And the very cool thing is that OpenAI released a Python environment, like an abstraction of of an environment, right? So what is an environment? You need an observation, you need actions. They did that abstraction, and they called it OpenAI Gym. And which means that if you want to have your algorithm, a new reinforcement learning on your problem, you just need to implement the environment using that API, and then you can use one of the stable baseline to solve your problem. So it's very easy to get started. And yeah, so that's rather exciting. I will get back to it later, because this is actually not going to work on the problem that I'm going to show later. So all these fancy algorithms will not work. Okay, so what is deep reinforcement learning that I'm going to focus on a bit more? That came out in 2015 with, again, a paper from DeepMind. So it was kind of a revolutionary paper where they said, okay, we always did reinforcement learning with kind of traditional methods. Now we just add deep learning to it. And how do we do that? And for which problem? So the problem was, okay, let's develop a reinforcement learning solution that can play all kind of Atari games. This is Arkanoid, is one of the games that they demonstrated their solution against. And yeah, basically they learn to play any kind of video game. So the input to the agent, the observation, was just the RGB image that was coming out from the video game. And the actions were just the position of the joystick or the press of the button. And so this is actually an example of what the agent learned to do. This is just one game. And you can see that he's actually learned to do a very nice trick, that he learned to put the ball on top of the line of blocks so that he's very efficient in playing the game. So that's actually a funny thing. Also, there is some very nice videos on YouTube where you can actually see that the agent learns this behavior after millions of play. As I said, it's very sample inefficient, means that you really need to do a lot of examples. But that's a very cool one. So how is this implemented? So as I said, you get as input your RGB image. And then what you just have a bunch of convolutions that you learn, right? So if you are, familiar with deep learning, it's just a combination of a series of convolutional operators that you learn over time. And then you go just to neurons that are activated. So basically you just, well, let's say you can just think about these as vectors, and you just learn operations to go from one vector to the other. But at the same time, you can just see this as a black box that matches the input to one of those operations, like the joystick operations. Go up, left, right, up, and push a button. And then what we do, we just train with this trial and error, and we try to optimize our agent. And then you also have a very cool thing that you can do. You can also try to understand how the agent is thinking. And that was actually in this original paper. I find it very cool. Each point here is one state, one observation, one state in the game. And you can see that, and they are close together if the agent thinks they are similar in terms of context in the game. And they are called according to the value, the notion of value. How valuable is this position? How much close I am to winning? And you can actually see that there are some groups, and they correspond to similar position on the board. This is Space Invaders. And you kind of have a map of how the agent is thinking. And you can also see that has this kind of group of states that are not considered valuable, so you're probably going to be losing soon, and others that are pretty valuable. And so you just train these, and that's pretty cool. Now, okay, this is all good. I mentioned you can just implement your own environment. You can reuse the stable baselines. Let's see a case where this actually doesn't work, because there are some reasons, and I'll get back to that later. And I'll use the bot-bow competition as an example. This is if you want to dive a bit deeper in it. It's all in Python. It's all available online. You can play with it. So what do we play on? So it's bot-bow is based on the Blood Bowl board game, which was published in 1986. It's a rather complex board game with a lot, actually, of video game implementations. So we are close to the third one. It's very complex. The whole point is like simulating on a board an American football game in a fantasy setting, which means that you also have different races that are playing, like elves, orcs, humans, and so on. And the rule set is rather complex. And it was a competition at the IEEE COG, which is the biggest conference on artificial intelligence for gaming. And at the third edition, there were basically no machine learning bot that can actually compete in that. So basically, just a scripted agent was much better. And what's the reason? OK, so the game is basically like this. You have your pieces on the board. You have 11. You play for 16 turns. And you just have to score a touchdown. And the other player is playing against you. There is some randomness in the game, which is you can, for example, try to block an opposing player, but then you have to try to roll a dice, and you only have 50% chance to actually, let's say, put the other player piece out of the game. You also have the ability to dodge. But also there, you have to roll a die. In this case, you have a 50% chance that he's not going to throw. Also, you have to throw the ball, and you can. And also there is a lot of randomness. The problem is that every time you fail an action, you basically lose a turn. So this means that this is a very risky game. You have to do a risk management. And also, you are punished very harshly if you fail an action. And on top of that, if we see the number of actions that you can do from one turn to the other, in chess you have roughly 30, in Go you have 300. For this game you have 10 to the power of 50. So the space of possibility is so huge, and what I said before, you train a reinforcement learning agent by trial and error, but every time that you fail, you are completely out of the game for 1/16 of your game. Yeah, it's difficult to learn. And so so this is kind of an idea of the input space, a lot of different actions, where that's basically what the agent can see. and we have 20,000 possible input scalars, and we actually take possible 8,000 actions. So it's, again, the message is all of this is really huge. Yeah, just as I said, no machine learning bot was able to compete in this in the past. So some approaches use curriculum learning. The idea is that you try to make your board game smaller and try the agent to be able to learn in this smaller setting. But indeed, these were not able to beat a scripted bot, where you had some kind of human defining how the bot should play. All right, so how did I kind of solve this in a way? And actually we won with this MimicBot the latest bot ball competition against scripted agents. So this is really the first and only machine learning based bot that actually can play in this game. Yeah, just a couple of things. I don't have too much time. I will just show the architecture. I will not dive into that. But I just want to play a bit how we can combine behavioral cloning together with reinforcement learning to improve sample efficiency and yeah, indeed solve this problem. Okay, so for the model architecture, I think I will not go too much into detail here. This is like the deep learning solution that I have. The cool thing here is that it uses something called channel attention to actually be able to preserve spatial information that is actually quite relevant in the game. Again, I will not go into it. I just want to mention that usually when you think about deep learning, you think, okay, it's something that I need to run on a big GPU and it takes a lot of time. Actually, this one is rather very optimized. It takes only 20 milliseconds to run on a laptop CPU. And so that was part of the equation. But I don't want to focus on the model itself. I want to say how we can actually train it. And if we go back to this picture, what you can do, we don't have a human expert because I could not play this for an infinite amount of time for the imitation learning. What I can do, I can take a scripted bot that was actually doing relatively good before and just collect how they can play. And I can just do imitation learning for a scripted bot. And now if I just let two scripted bots play against each other for, let's say, 200 games, I can collect the states and the actions and just then train a classification model to predict the actions. And if I do that, I can actually see that the bot that is trained here, the behavioral cloning one, can actually beat the random one all the time, and it can actually beat the scripted one, let's say, at least win here against the scripted one, let's say, of the time. And before, basically, every machine learning model was always losing. And of course, here is training. There is a bit of overfitting. Again, I will not go into detail here, but we train our model using behavioral cloning. But of course, we cannot expect to beat all the time the agent that is trained against, because we are just trying to imitate. So what we can do instead is say, okay, we just train with behavioral cloning. We have the model, is doing okay-ish, and now we start doing reinforcement learning. We just do some pre-training with behavioral cloning, and then we do reinforcement learning. Unfortunately, that doesn't work, because you have something that is called policy collapse. So your model, the behavioral cloning, is not able to adapt to the new training environment. So here you see the reward, and the winning rate at the beginning, it was high, so it was playing against the scripted bot and winning 40% of the time, and after a bit of training is always losing. It's called policy collapse, and we need to find a way to actually counteract that. And the trick here is that we can actually combine the two. We can do a reinforcement learning for a number of iterations. We update our model, then we go back and we still use the information from behavioral cloning. And if we do that, we can stabilize our training in such a way that we can start learning to act in a reinforcement learning way in this environment. But of course, we are still grounded to the original scripted bot behavior. So, but after a while, we can just do, here should be a reinforcement learning update. We can just do a reinforcement learning update. And now our win rate goes up. So we overcome the initial drift and I'll be finished soon, by doing this trick. Here, actually, you see, yeah, I'll not go into this. I don't have time, I'd say. But as I said before, there is a way to inspect actually what's happening in the network, so that you can really dive into that. And also, as I said, I also skip that. So we have some very hybrid behavior, right? So you can also use some scripted action together with your model. And yeah, so it actually won the competition. As I said, all basic stable baseline do not work. That's also why you could see that not so many people competed, because like existing works do not work in this setting. And just to conclude, I would say, to me, the cool thing is that if you have a problem where you can actually simulate and you have your, let's say, control theory algorithm that already works, you can kind of model the imperfections of your model using this approach, right? So you just add an extra bit of control. You use your traditional algorithm as a way to ground your solution, and you just use this trick to just try to simulate and get a bit better, right? So, and that's really flexible, because also you don't have the human in the loop, right? So, and with that, I think it's better if we leave some time for Q&A.
I knew it.
So, cool talk, thanks. A lot of these reinforcement learning demos, they're pretty cool because they're all about video games. But then you also kind of wonder, well, a video game, it's a simulator, you kind of have the perfect simulation, which is still a really cool demo, but like then the question is, how's that going to be turned into a practical application? Yeah. Any comments on that?
Yeah, that's why I showed the one from OpenAI with the manipulator, because that was an attempt. There was also a lot of controversy about this one, because they kind of cheated in a way. They had a lot of extra sensors then to do the translation. Yeah, I think the need for the simulation environment and how accurate that is, it's super crucial. If you don't have that one, well, you're, excited. At the same time, you can also see, I mean, translation to the physical world is difficult. That's the thing. But you can actually simulate a lot of digital stuff very accurately, and there it's where it can shine a bit more, right? So, but indeed, I see the problem, right? So, and I was also at Philips is a topic of interest, but also there, if you have let's say an imaging device, then you need to simulate that, right? So, and that's the tricky thing, yeah.
Any other questions?
Thank you very much for the presentation. So a question which is related to the previous question. If, for example, we have behavioral cloning for different users, for multiple users, do you think that this would help our reinforcement learning later? Because then you can even group users together and, for example, identify patterns between users and, I don't know, kind of boost your reinforcement learning algorithm.
Yeah, absolutely. I mean, that depends on your policy, let's say the policy network. So if your policy network is able to model the behavior of different agents, then yeah, just go for it, right? So the question is your policy able to represent subpopulations of users? And that's why deep reinforcement learning is actually rather popular, because it can do that, right? So it can adapt, you can, well, it's just a high dimensional space where you act in.